There is a planet orbiting the star closest to our sun, right now, as you watch this. It has been there for billions of years, spinning quietly, 4.24 light-years from where you are sitting. And in July 2025, a brand new instrument at a Chilean observatory called NIRPS confirmed it again. More precisely than ever before, Earth-sized. In the habitable zone, the nearest known rocky world outside our solar system. We know exactly where it is. We will never reach it, and the reason has nothing to do with money, or politics, or lack of trying. The reason is physics. The kind of physics that doesn't negotiate. "4.24 light-years. Say it slowly. 4.24. It sounds almost reachable. Like something a determined civilization should be able to cross. Here is what that number actually means. Light moves at 300,000 kilometers every single second. In 1 second, it circles Earth more than 7 times. In 8 minutes, it crosses the entire distance from the sun to us. In 1 year, it travels 9.5 trillion kilometers. Multiply that by 4.24. The distance to Proxima b is roughly 40 trillion kilometers. Written out, 40 trillion. Now let's compare that to something we actually built. The Parker Solar Probe is the fastest human-made object ever created. At its peak, it reaches 692,000 kilometers per hour, a speed so violent that it makes a rifle bullet look stationary. At that speed, pointed directly at Proxima b, it would arrive in approximately 6,500 years. Not 65 years. Not 650 years. 6,500 years. The pyramids of Egypt were built roughly 4,500 years ago. We would need to wait longer than all of recorded human history, 1.5 times over, just for the fastest thing we've ever made to reach our nearest neighbor. That is the first wall, and it is not the biggest one. To make any real progress, to reach Proxima b in decades rather than millennia, a spacecraft needs to hit at least 10% of the speed of light. 10% sounds modest. It is not. 10% of light speed is 30,000 kilometers per second. In 1 second at that speed, a spacecraft would cross the distance from London to New York, 26 times. The entire diameter of Earth passes in less than half a second. Now, how do you get there? Every rocket ever built works on the same principle. You throw mass out the back to push the spacecraft forward. It works beautifully at human scales. It collapses completely at interstellar ones. Here is why. The faster you want to go, the more fuel you need. But fuel has mass. More mass means more fuel to accelerate that fuel. It becomes a loop, a mathematical trap, that makes reaching interstellar speeds with chemical rockets essentially impossible. To send a crewed spacecraft to Proxima b using rocket propulsion, carrying everything humans need to survive for decades, food, water, medical systems, radiation shielding, spare parts, engines, the fuel for slowing down. The fuel requirements become larger than anything physically launchable. Not expensive. Not difficult. Physically impossible. In 2016, Stephen Hawking and billionaire Yuri Milner stood on a stage in New York and announced something extraordinary. Breakthrough Starshot, a $100 million initiative to send tiny laser-propelled probes to Proxima Centauri at 20% of the speed of light. The idea was elegant. No fuel on board. Just a gram-scale nanocraft attached to a sail. A 100-gigawatt ground-based laser array fires for 10 minutes. The sail catches the photons. The craft accelerates to 60,000 kilometers per second and coasts to Alpha Centauri in roughly 20 years. It made headlines around the world. Here is what happened next. The project spent approximately $4.5 million out of the $100 million pledged, spread across 30 small contracts over 9 years. In September 2025, Scientific American reported what many in the scientific community had quietly known for years. Breakthrough Starshot is on indefinite hold. Possibly over. Not because the physics was wrong. The physics was real. Because the engineering problems were brutal. A 100-gigawatt laser array doesn't exist. Building one requires technology decades away. The nanocraft needs to survive not just the acceleration, 10,000 times the force of gravity for 10 minutes, but decades of interstellar travel, bombarded by radiation and dust particles that, at 20% light speed, hit with the energy of small explosions. And then, it cannot stop. A flyby lasting minutes. A signal taking 4 years to reach Earth. No landing, no orbit, no return. The most ambitious space project in history quietly faded away. Not with a press conference. Not with an announcement. Just silence. Let's say we solved everything. Propulsion, shielding, deceleration, all of it. After decades of travel, the spacecraft enters the Proxima Centauri system. And there it is, Proxima b. What are you actually looking at? Proxima b orbits its star in just 11 Earth days. That closeness means it sits in the habitable zone, the right temperature range for liquid water. That is what made it famous. That is why it dominated headlines in 2016 when it was discovered. But here is what habitable zone actually means. It means one thing: the planet is the right distance from its star for liquid water to be possible. That is all. It says nothing about whether liquid water exists. It says nothing about atmosphere. It says nothing about radiation. And Proxima Centauri is not a peaceful star. It is a red dwarf, smaller and cooler than the Sun, but violently active. It regularly fires massive stellar flares directly at Proxima b. A 2025 study using the new NIRPS spectrograph at La Silla Observatory in Chile confirmed the planet's existence with greater precision than ever before, but also highlighted that variations in the planet's signal make atmospheric detection extremely difficult. We cannot yet determine if Proxima b has an atmosphere at all. There is also the tidal locking problem. Because the planet orbits so close to its star, it may be permanently locked, one face in eternal daylight, one in eternal night. If it has no atmosphere to redistribute heat, one side bakes and one side freezes. We spent 40 trillion kilometers getting here, and we may have found a dead rock. Or, and this is the part that keeps scientists up at night, something stranger. A twilight zone between permanent day and permanent night. Thick clouds, underground water, conditions we haven't imagined. We genuinely do not know. So what does a realistic path to the stars actually look like? Nuclear pulse propulsion, using controlled nuclear explosions for thrust, could theoretically reach 10% of light speed. But it requires building and detonating thousands of nuclear devices in space, which presents obvious political and engineering nightmares. Fusion drives, using the same reaction that powers the Sun, could be faster still. But after 70 years of fusion research on Earth, we still haven't achieved a sustained, net-positive fusion reaction in a power plant. Building a fusion engine compact enough to launch into space remains a generation away at minimum. Antimatter propulsion is theoretically the most powerful option, the most energy-dense fuel physically possible. The problem: we produce approximately 1 nanogram of antimatter per year globally. A crewed mission would require grams or kilograms. At current production rates, that would take longer than the age of the universe to accumulate. Generation ships, spacecraft designed for crews to live and die across multiple generations, solve the time problem by accepting it. You don't arrive. Your great-great-grandchildren do. The philosophical, ethical, and engineering challenges of sustaining a closed human civilization for centuries in a sealed metal container remain almost entirely unsolved. None of these are science fiction. They are real physics. Here is the honest truth about Proxima b. It is 4.24 light-years away. That number is both an astronomical whisper and a civilizational scream. Close enough to study, close enough to confirm, close enough that in July 2025, a new telescope confirmed a smaller companion planet orbiting the same star, Proxima d, making the system even more interesting than we thought. And impossibly, cosmically, humblingly far away. We cannot reach it because we are still a young civilization playing with chemical fire at the edge of our own solar system. We cannot reach it because the gap between planets and stars is not a challenge of engineering. It is a challenge of kind. A fundamentally different category of problem than anything we have faced. Voyager 1 has been traveling for nearly 50 years. It has covered 0.002% of the distance to Proxima Centauri. And yet, Proxima b does something for us that no reachable destination can. It tells us where we are in the story. We are not near the end. We are barely past the beginning. The species that walked out of Africa and crossed every ocean and landed on the moon and sent machines to the edge of the solar system, that species has not yet taken a single step toward the stars. Proxima b is not a destination. It is a reminder of how much further we have to go.